All right, so this is part 2 of electron configuration, and we're going to get into now filling up our different orbitals with electrons. So that's good. So electron configuration is basically a notation system that we're going to use to describe where all the orbitals are, where all the electrons are in the orbitals. Okay, we're going to use this principle called Aufbau principle, which basically just means building up. Okay, it's a German word, and it's going to tell us the filling order for the electrons in the orbitals. All right, and in this course, mostly we're concerned about the ground state electron configuration. So this is the lowest energy configuration. So if you just have, an atom floating around, what is its lowest energy configuration? That's, most of the atoms are going to have that electron configuration. Now, if you shine light on it, you heat it up, okay, then it's going to change the electron configuration. Some of those electrons are going to get excited, like we talked about before when talking about the Bohr model. Same thing here. But, for this course, most of the time we're going to be talking about ground state electron configuration. Take other chemistry courses and you'll learn about excited state configurations. And that's super interesting because you can then learn about, how light can interact with matter and how that happens. And you'll need to know excited state electron configurations for that, okay? So the period tells us the energy level. I mentioned that a few videos ago. Basically, that's the principal quantum number is the rho. Rho and period are the same words, two words for the same thing. Periodic table, okay? I guess I could call rho table. It doesn't sound as good. And so the location on the table tells you something about the shape, right? And we said that the shape was the L value, SPDF orbitals. And so each orbital can hold 2 electrons, and electrons must have different spins. That's how each orbital can hold 2 electrons, okay? And so basically, for every element on the periodic table, there's an electron configuration, and you can go through and say where those electrons are in the ground state, what different orbitals are there. So for example, you look at hydrogen here, that's the first one, right? Its electron configuration is going to be 1s1. There's 1 electron, it only has 1 electron in the first orbital, the ground state orbital, which is the 1s. Then you're going to go to helium, number 2. Well, that's going to have 2 electrons in the 1s, a spin up and a spin down. That's why there's a superscript 2 here, okay? And those 2 are going to also be present when you get to lithium. You're going to have an electron configuration of 1s2, 2s1, okay? You're going to have the next highest energy orbitals at 2s. And so you can keep on going through here, and we'll do a lot of examples on these in the upcoming videos and slides. But for now, I just want you to get this idea that the shape of the periodic table comes from quantum mechanics, guys. It comes from quantum mechanics, and it comes from electrons filling up in the ground state of the orbitals, okay? So this is really, really neat stuff. So this Aufbau principle tells us how to do this filling, and it's basically all that information is on the last slide. But you're going to put 1 electron in the 1s. You're not going to then jump to a 2s. That would be an excited state. You want to fill it up. Fill up that 1s first. So you're going to be at the 1s2. Put it with a different spin. Of course, this is a 1s orbital, so they're both going to have n equals 1, and it's an s orbital, so L equals 0. M sub L is then going to have to be equal to 0. Those are types of things you're going to have to know, and you're going to have to get used to these quantum numbers. All right, but the spin up and spin down, you're going to have those. And so we can also draw this like this, right? An orbital diagram, spin up. We could have also drawn spin down, doesn't matter. But for helium, we're going to have 2 electrons in the 1s, so we're going to have a spin up and a spin down. So the last sort of rule we need to know is called Hunds Rule. This is also called the seats on the bus rule, or at least that's what I call it and some other people call it. And what I was going to do in class was have 2 people, volunteers, randomly picked, okay, of you guys. And I was then going to have 4 chairs set out, okay, 2 and 2, like it was a pretend bus. And I was going to tell both of those 2 people to sit down. And what would have hopefully happened, or has always happened in years past, is that those two people won't sit next to one another. And now with coronavirus, right, definitely they're not going to sit one next to one another. Okay, so it's easy to remember. But this is trying to tell you, like, okay, these two chairs represent the two different spins, and this is an orbital. And the electrons would rather be in another orbital, okay, if it's the same energy, than be next to one another. You don't want to be next to one another. Hey, electrons are negative, right? So if two negatives are close to one another, they're going to repel. That's going to be energetically unfavorable. So this is called Hunds Rule. If two or more orbitals with the same energy are available, we call this degenerate. Degeneracy means same energy, okay? If they're degenerate orbitals, they have the same energy. One electron will go into each orbital until the whole degenerate orbital set is half filled. And all of the electrons in that half-filled set of degenerate orbitals will have the same spin quantum number. That may sound very complicated. It was a long paragraph there describing what Hunds rules is. It's easiest just to see it, okay, with an example. So take nitrogen, okay? Nitrogen has 7 protons, okay? It's 7 on the periodic table. And so its electron configuration is going to be 1s2, fill up 2 electrons, spin up, spin down in the 1s. Next, you go to the 2s, spin up, spin down. Then you go to the 2p. Well, now you have 3 orbitals. You could possibly put 6 electrons in there, but you only have 3 more electrons in nitrogen. Okay, electrons number 5, 6th, and 7th, the 5th, 6th, and 7th electrons. Where are you going to put those? Why are there 3 orbitals, first of all? Well, m sub l equals -1, 0, and +1. 3 different orientations, the px, the py, the pz, all words for the same thing. Okay, so we represent that as 3 lines that can hold a total of 6 electrons, but we only have 3 electrons. You're going to put them in seats on the bus rule. They're going to go on same spin, but they're going to go in different orbitals. They want to maximize the distance that they are apart from one another, minimize electron-electron repulsion. That's what a Hunds rule is. So you're going to go spin up, spin up, spin up, all in 3 separate orbitals. Now you could have gone spin down, spin down, spin down. That's the same, okay? That's mathematically equivalent. But you would not want to put a spin up and a spin down. That would be an excited state that's higher energy, okay? So you want to be spin up, in separate orbitals. Now, if you had a 4th electron, you went from nitrogen and you went to oxygen on the periodic table, then you'd be forced to go spin down in one of these orbitals, okay? But Hunds rules tells you that these are all going to be unpaired electrons, okay? And they're all going to have the same spin, all spin up, or you could write it all spin down. Let's just do all spin up, you know, just for consistency. All right, so the last thing that we have to go over is I wanted to do an example, and I was going to show this on the board if we had gotten that far in class, but we didn't in the in-person meetings. So let me go to the whiteboard and share the whiteboard with you. And so now, oops. Still trying to figure out all this stuff. Okay, there we go. We're in action. Sorry, guys. Okay, so sulfur. I wanted to give you different electron configurations. So the general electron configuration is sulfur. We're going to put 1s2, 2s2, 2p6, okay, for filling up the p. This is sulfur's in 3rd row if you look at your periodic table. 3s2, 3p4. So that's a total of, what's that? 2 plus 2 plus 2 plus 2 plus 6 is 10, 16 electrons. So sulfur is number 16 on the periodic table if you look at that. And so let's draw that out. What that would look like would be 1s, 2s, 2p. Now there's 3p orbitals, 3 different orientations, 3s, and then we have a 3p's. And I wanted to give you some different possible orientations here. And what I'm going to want you to do is figure out which one of these is the correct ground state. Okay. So again, this is 1s, etc. Okay. These are the 2p's, 3 2p's. This is the 3s, holds 2 electrons, and 3p's each can hold a maximum of 6 electrons. So we're going to spin up, spin down. These are all filled. Okay. Spin up, spin down, spin up, spin down, spin up, spin down. All right, but now the interesting part is do something like this. Okay. Okay, so which of these would be correct ground states? Or maybe there's more than one answer. So let's look at this. Well, we want to satisfy Hunds rule. Now, the first thing to say on all this stuff is, well, look, they all have 16 electrons. They all add up. The 1s to the 3s business, all these, they're the same. Those are all just filled. The differences occur in the 3p's. So let's look at the 3p's. We have 4 electrons in all of them. That's cool. And we're unpaired. Unpaired, we would fill it up. How do we fill it up? We should fill it up, up, up 3 electrons, and then a 4th electron. That's kind of what we would want, right? And so none of them are like that, but you can see that this one's equivalent. I just put the 4th electron in a different orbital. Didn't really matter, but I have still the 2 unpaired electrons. So fundamentally the same. It's 2 unpaired, right? And 1 paired. But then look at this one. This one is wrong because they're not unpaired. We have no electrons there. That's not the seats on the bus rule. The electrons aren't as far apart as possible there. Okay, so that is not going to be a happy situation. So anyway, that's the end of this video, and we'll continue with some more examples in the next videos. All right, thanks guys.